Let's jump right into this explainer. Today, we're diving headfirst into the fascinating world of molecular architecture. We're going to take what looks like an incredibly dense, frankly chaotic chemical reaction scheme, and we're going to demystify the whole shebang. We'll turn that intimidating jumble of letters and shapes into a really straightforward, step-by-step molecular recipe. Now, at first glance, the complete chemical blueprint for synthesizing macrocyclic vanadium complexes looks incredibly intimidating, right? It's kind of like staring at an alien language or some impossible wiring diagram. But stick with me here. I promise you, by the end of this explainer, you're going to perfectly understand every single part of this blueprint. We are going to decode it together. Here's how we're going to break it down today. First, we'll look at the chemical blueprint. Then, step 1, the intermediate, followed by step 2, the macrocycle, and finally, we'll talk about customizing the final product. Easy enough, right?
All right, let's kick things off with section 1, the chemical blueprint, the absolute foundation of our synthesis.
So, before we start hypothetically mixing chemicals, we've got to know what we're actually building. The key takeaway here is understanding that a macrocycle is just a really large ring-shaped chemical molecule. This ring structure, that represents the final completed state of our synthesis. Think of it like a closed circular track built entirely out of atoms. That's our ultimate finish line today. Now let's treat this first step like a quick game of spot the difference. Look closely at the starting materials for our two parallel pathways. The top pathway uses a molecule with a furyl ring. That's a ring with an oxygen atom in it. But the bottom pathway, that one uses a thionyl ring, which swaps in a sulfur atom instead. Other than that one tiny structural difference, the rest of the starting molecule is exactly the same. We're just picking a slightly different foundational building block to see how it shapes our final structure down the line. Moving right along to section 2, step 1, the intermediate. This is where we start building the framing. You know, in chemistry, an intermediate is essentially a temporary middle stage complex. You'll see them labeled in our diagram as IA and IAA. They form during a chemical reaction right before becoming the actual final product. Imagine you're building a house, right? The intermediate is the structural framing. The walls are up, the foundation is solidly set around our central atom, but you haven't put the roof on just yet. It's stable enough to stand, but it definitely isn't finished. To make this whole process super easy to follow, we can actually break that overwhelming diagram down into a really simple two-step checklist. Step 1 involves adding VOSO4-3H2O and p-phenyldiamine in a solvent called ethanol, or ETH. Step 2 is simply going to be adding the beta-diketone. So let's zoom in on that first step, the reaction in ETH that actually builds our framing. Starting over on the left, we can see this first step in action. We take our starting molecule, we introduce VOSO4, which gives us that crucial central vanadium atom marked with a V, and then we add 2 molecules of p-phenyldiamine in ethanol. Watch what happens here. The molecules literally snap together around that central vanadium atom to create our intermediate framings, IA and IA. And I really want you to notice those red NH2 groups hanging off the bottom there. Those are exposed connection points, basically waiting for the next piece of our puzzle. Our framing is up, and it is ready for the roof. Which brings us perfectly to section 3, step 2, the macrocycle, where we focus on closing the structure. Okay, so looking at those exposed red NH2 groups just hanging at the bottom of our intermediate, the million-dollar question is, how do we actually close this molecular ring to finish the structure? How exactly do we seal that gap? Well, the answer is step 2 on our checklist. We add the beta-diketone. This is absolutely the chemical equivalent of lowering the roof onto our house. By introducing the beta-diketone, it reacts perfectly with those exposed NH2 groups, beautifully bridging the gap at the bottom of the molecule. This single, crucial addition transforms our open, temporary intermediate into the final closed-ring macrocyclic complex, which you see labeled as IB and IB. Just like that, we've successfully completed the macrocycle. And finally, let's hit section 4, customizing the product. This is where we get to play molecular architects. Remember that beta-diketone roof we just lowered to close the structure? Well, it actually has 2 modular slots attached to it, labeled R and R'. And by swapping out what we plug into those R slots, we basically act as chemical customizers. For instance, plugging in 2 CH3 groups gives us acetylacetone. Using a C6H5 and a CH3, that gives us benzoyl acetone. It's completely modular and entirely up to the architect. It's a real game changer. To summarize, our specific customization options for the beta-diketone roof include acetylacetone, benzoyl acetone, thionyl trifluoroacetone, and dibenzoyl methane. Each one creates a slightly different final macrocycle with its own unique chemical properties. What this proves is that what we've been looking at isn't just one static recipe. It's a highly versatile template for tons of different molecular creations. Let's bring that full diagram back on screen for just a moment. Look at it now. It's no longer an intimidating mess, is it? You can easily read this blueprint from left to right. You see the starting blocks over on the far left, you see the ethanol reaction right in the middle that builds the framing around the vanadium to make our intermediate, and then you see the addition of the customizable beta-D ketone roof on the right that snaps the whole thing shut into a finished macrocycle. So the really crucial point I want you to take away today is the sheer modularity and logic of this whole process. It leaves us with a truly fascinating question. If changing just one single R group completely alters the final molecule, what other totally unimaginable structures could molecular architecture build next? The Lego-like possibilities of chemical synthesis are honestly endless. Thanks so much for joining me on this explainer, and keep exploring.